Welcome everyone to the annual Bok Prize Colloquium. I should say that the great granddaughter of Bok is here with us, Kenzie Bok. Last year she was just about to receive her PhD at the University of Cambridge, is it? And she's now a doctor. And she's named
What field?
History. Which does relate to astronomy. If you start early enough, you will get to the history of the universe. And that's actually related to what will be discussed today. And so let me say a few words about the Bok Prize. It's a gift of an anonymous donor to establish a prize in honor of Professor Bart Bok. And in his name, the income to be used for a prize to be awarded, preferably biannually, on the recommendation of the astronomy department, to a recent holder of a PhD degree in the physical sciences from Harvard, who is under 35 years old. Generally speaking, there is a preference for the area of Milky Way research, but it's not enforced in all cases. And I should say we have a very distinguished list of recipients of the Bok Prize, and every time I look at it, it's quite remarkable. There are many names here, 3 Nobel laureates that you all know, Joe Taylor, Brian Schmidt, and Adam Rees, and many other very distinguished astronomers, some of whom are at the CFA. I mean, Andrea Dupree got it in 73, Joe Silk, Frank Shu, Josh Grindley got it in 76, Sandy Faber, 78, Bill Foreman and Christine Jones, 79, Charlie Lada in 82, Mark Aronson, 83, Len Cowie, 84, David Sperger, 94, Alisa Goodman, 98, Lincoln Greenhill, 99, and Jimmy Herrenstein. And the list goes on. Brian Schmidt, Adam Rees, Dave Charbonneau and Sarah Seeger got it the same year. Elliot Quatert, Scott Ransom, Warren Brown, Steve Forlanetto, Jenny Green, Ferial Ozel. All of these recent names we all know because they are very active these days. Sarab Jha, Heather Knudsen, Phil Hopkins, Dan Maroney, and Brant Robertson, Meredith Hughes, and this year's recipient is Matt McQuinn. And so let me say a few words about the prize, or about the career of Bart Bok before we describe the work of Matt McQuinn. So Bart Bok was born in 1906. He was a Dutch-born American astronomer, teacher and lecturer. And he's best known for his work on the structure and evolution of the Milky Way galaxy and for discovery of Bok globules. These are small, dense, dark clouds of the interstellar medium that include dust and that are seen in silhouettes against bright backgrounds. And he suggested that they may be in the process of contracting before forming stars. In 1929, he finished his thesis studies at Groningen and moved across the Atlantic to Cambridge, Massachusetts on the invitation of Harlow Shapley, the director of the Harvard College Observatory. And 2 days after moving to the US, he married Priscilla, who was also an astronomer, after whom her great-granddaughter is named. And the Boks remained at Harvard University for almost 30 years, from 1929 to 57. Bart Bok taught astronomy, and he was the director of the Harvard College Observatory. So there is a long history. In 1957, the Boks moved to Australia, where he became the director of the Mount Stromlo Observatory at the Australian National University, ANU, in Canberra, where he was for the next 9 years. And he was a pioneer of the use of electronic computers for astronomical observing. and the first person to use computers for any purpose at the ANU. So today's recipient of the Bok Prize is Matt McQuinn. Matt was a PhD student in our department in 2004 to 2009. He was advised by Lars Hernquist and did a spectacular job in studying the intergalactic medium, in particular the thermal history of the intergalactic medium from very early times, about 1 billion years after the Big Bang, as the medium was heated by stars and mostly quasars at late times. And he also worked on a way of probing the intergalactic medium when it was still neutral, using the 21 centimeter line of hydrogen, analyzed properties of the medium in novel ways. He moved to a postdoc at the University of California at Berkeley in 2009 and was there until 2012 when he accepted a faculty position at the University of Washington in Seattle. And that's where he is now. And given his major accomplishments and contributions to our understanding of the intergalactic medium, we would like to offer him the Bok Award. He's one of the most successful students that went through the theoretical astrophysics division of the Center for Astrophysics. So I would like to invite Mackenzie to give the award, and there is also an envelope here to Matt.
Great. Thanks so much.
Thank you so much.
Congratulations. Do we take a photo? I thought I should say very quickly.
You can. Why don't you go center stage?
So, as he said, my name's actually Priscilla Mackenzie Bok. So I have a different middle name, but the same name as my great-grandmother, and have grown up very much with the stories of their astronomy together. It's somewhat crazy to get your PhD as a young woman and only be the second person with a PhD with your name, and the first one got it 95 years ago. Priscilla was astonishing, and so was Bart. And I just want to say it means a lot to our family to keep coming back and be involved in this, even though, obviously, alas, we've strayed out of astronomy. But one thing that resonates a lot for me about the stories of my great-grandfather, now that I'm also in the academic world, is that he was superlatively good at research, and that's really what this occasion is honoring, but that he was also an exceptional teacher and a public astronomer. And I think in history also, in academia, we think about sort of that three-legged stool and how do we, without compromising on the importance of research, really think about public engagement and teaching as well. And so I hope he continues to be a model for that in astronomy. He's certainly a model of that to me as a historian. So thanks so much.
And we wanted to give a small gift to you and your father.
Thanks so much.
Thank you for coming. I hope you will enjoy the colloquium. Matt.
Try to follow.
Thank you, Avi.
You're wired, right?
Oh, wait. Yeah, I should be, yes.
Okay, go ahead.
Okay. Oh, thank you so much. It's a total pleasure to be here and back and see everyone. It's been a while since I've been back at Harvard. And so, as Avi said, I did my PhD, and a lot of the concentration was on reionization and the thermal history of the intergalactic medium. And this is actually the talk since leaving Harvard that I think is closest to the work that I did on my PhD, and I think it largely motivated by some recent observational results. And so as Avi alluded to, this talk is also a talk about the history of the history of the universe. And so, as many of you guys are familiar, or all of you are familiar, we have these beautiful images of the sky in the microwave, where we see the universe when it was a few 100,000 years old. And we're able to measure the temperature of the radiation to fantastic precision, and even map out the fluctuations at this point almost as well as we ever can. And so at that time, we're seeing the universe when it's recombining. That's why the photons are able to make it to us. And for a long period, the universe is, let me find a pointer. The universe is neutral. And then at some point, the first stars and galaxies form. They produce ionizing photons. And the universe becomes reionized. And we can again see or measure the temperature of the intergalactic medium, which I guess this is temperature over here. This is neutral fraction, with the Lyman-a Forest. And so that will be a theme of this talk. So I'm a bit jealous. Like I went to the Konstantin Batigan talk earlier on the ninth planet, and I'm jealous that in planetary science, it's very easy to understand the concepts, and all of us know planet going around star, and kind of have an idea or have a basic some of the basic tenets in our minds. For Lyman-a Forest, probably most of us know what the Lyman-a Forest is, but I think it's always a good idea to start off with a summary of, or just a quick synopsis of what it is, just in case you're not familiar. And so the Lyman-a Forest, this is a quasar, so this is a backlight. And I'm going to play a movie in a second. This movie's from a really neat movie that Andrew Ponson made. And so we're going to follow the light from this quasar as it travels through the universe, mostly through the intergalactic medium. And so this is the spectrum of that quasar. And as it travels, it's redshifting because the universe is expanding. But it encounters gas at different points while it has redshifted a certain amount. And at those points, then you get a forest of absorption lines. Because the universe is mostly hydrogen, the hydrogen is most prominent, but other lines can also be important. And so I'm going to play the movie. And so here, we're quasar light, we're traveling through the universe. And when we hit something dense, we get more absorption. This is the Lyman alpha resonance. There's other Lyman resonances of hydrogen. Go through a galaxy, you get a ton of absorption. And then certain regions of the universe have metals. These are metals. And so that's what the Lyman-a Forest is. And you're going to see a lot of Lyman-a Forest spectra, or I will allude to the Lyman-a Forest several times throughout this talk. And I think it's nice to put work in context. And so let me start off with a brief synopsis of the history of the Lyman-a Forest. So the same year that Penzias and Wilson discovered the CMB, 1965, the Martin Schmidt found a few quasars with extremely high redshifts. One of those quasars had a redshift greater than 2. And it was immediately pointed out by these people that there should be intergalactic absorption that for a quasar at redshift greater than 2 will have redshifted into the optical. So the Lyman alpha line will have redshifted into the optical. And if there's anything in the intergalactic medium, any neutral gas, then that neutral that neutral gas is likely to absorb the light from that background quasar. And if we put in modern values for cosmological parameters, greater than a part in 10 to the 5 of the hydrogen, if that is neutral, then you get a very large optical depth, and you would expect complete absorption. And so then the observers started looking for this, and in 1970, Roger Lenz found a redshift 2.8 object where there were multiple Lyman series lines of hydrogen that we're seeing. But it wasn't a complete absorption trough, as you would expect if the universe weren't highly ionized. And so this implied that the IGM must be highly ionized. And eventually the community coalesced on the idea that it must be photoionized. Collisional ionization never worked very well. It required too much fine tuning. Then jump forward to the 1990s. The Keck is constructed, and so we have a 10-meter telescope, and in particular the high-res instrument on Keck started to give us beautiful spectra, the first resolved spectra. Some of these spectra are just absolutely glorious, where at every pixel, a resolution 100,000, you have signal noise greater than 100. And then 1995, the theorists finally caught up, I would say. This is the time when the first hydro simulations were run in the cold dark matter paradigm. And Lars Hörnquist wrote one of the seminal papers on this. And with one of the first things that these simulations were applied to were the observations of the Lyman-a Forest. And it was realized very quickly that the models look almost exactly like the observations. And this is often pointed to as one of the great successes of numerical cosmology. And so then the ensuing years after 1995, I would say there was a lot of work on the Lyman-a Forest. People were very excited. And then things went a little dormant for a decade. And I'm happy to say that the research in this field has really gotten a lot more active in the last few years. And I point to a few reasons why this is the case. And so one of the reasons, especially for me, is that the observers that use these giant optical telescopes, they've often kept their spectra under lock and key. And that's becoming less of the case now. And so now I have a couple hundred high signal noise, high resolution spectra that I can just play with. And so the theorists or people who haven't taken these spectra now can look at things and measure whatever statistics they want. And then if 100 spectra isn't enough for you, then there are also almost 200,000 spectra that have been gathered with SDSS BOSS in the last few years, albeit of much lower quality than these Keck high-res spectra. And then the community has started to gather samples of higher redshift quasars. This is statistical samples, which is something that we're going to come back to in this talk. So I'm going to talk about absorption at redshift greater than 5. Something really interesting is going on, and I'm going to give you one explanation that I think may be right, and if it's right, is very exciting. And then it's always been super hard to run simulations of the Lyman-a Forest. You need to resolve these small absorbers. They tend to be of order 10 to the 9 solar mass regions in the universe. But also you need a large enough sample of the universe to be able to make converged statistical statements, and this always was hard. And I would say only in the last few years has it become really feasible to achieve the dynamic range that you need. And then to segue into the kind of the focus of this talk, I'm going to make a somewhat controversial statement that in the post-Planck era, so Planck is this CMB telescope where we've measured cosmological parameters to 1%. So we know, at least in our standard lambda CDM cosmology, these parameters very well. One of the most interesting quantities is that we can now measure from the Lyman-a Forest. It's going to be hard to compete with these cosmological constraints, but one of the most interesting parameters is the temperature of the gas in the intergalactic medium, and I'll try to justify why I think this is the case. Okay, so the outline of this talk is I'm going to develop models for the temperature of the intergalactic medium, and I hesitate a little bit to call these models because oftentimes I feel in astronomy, and I apologize if this maligns anyone's model, but that you can often tune your model to get what you want. For IGM temperature, the things are very robust. Like you can't do a lot, at least in our standard model, for how IGM temperature works. And so there's not a lot of tuning, and I'm going to justify the statement that can be done. And so I'm going to take these IGM temperature models, and then I'm going to apply them to a bunch of things. I'm going to apply them to interpreting some Lyman-a Forest measurements, some recent temperature measurements. I'm going to apply them to the Gunn-Peterson troughs in the Lyman-a Forest. So I mentioned before that there was this hypothesis in 1965 that there should be these troughs of complete absorption. And people looked, and they didn't, at least in 1970s and all the way to 2000s, and they didn't see these troughs. But when Sloan came around and we started finding redshift 6 quasars, these troughs, we finally found them. So above redshift 5.5, we start to see troughs of complete absorption. And I'm going to explain what I think these are telling us. then I'm going to apply these models to dwarf galaxies. Since so many people in astronomy are working on galaxy formation, I feel like making some contact with research in that field is like always gets the most excitement. And so I'm going to try my best to do that in this talk. I guess Bach, of course, specialized in Milky Way, as we've heard. And then I put this up just to like make you guys think I'm crazy. And also I was inspired by Konstantin's talk earlier. But unfortunately, I probably will not get to Planet Nine's habitability in this talk. Sorry, Dave Charbonneau, if you're in the audience. Okay, so this is a talk on the temperature history of the intergalactic medium. And so I'm going to give you kind of the standard story for what shapes this history. And so in the standard story, the principles are very simple. So here's a very early model for the thermal history of the intergalactic medium. This is a seminal paper, and one of the projects I'm going to describe is doing this in a more modern context, doing this type of modeling. Okay, so what are the principles that shape the thermal history of the intergalactic medium? So the first principle, and this is a principle that isn't very well appreciated, I feel. And so the first principle is that you have the first galaxies, and they're producing ionizing photons, and they're ionizing the gas in the universe, and so you have these ionization fronts that are sweeping across the universe. And heating up the gas. And so when this is happening, the universe looks like a Swiss cheese. There are regions that are almost totally ionized and regions that are totally neutral. And then these ionization fronts are very thin, of order a kiloparsec width. And it turns out that the temperature that the intergalactic medium is heated to by these ionization fronts is over. It can only have a very narrow. Can only take a very narrow range, and the reason for this is because. And this is even pretty. The temperature depends very weakly on the spectrum of the sources that are ionizing things. And the reason for this is at these ionization fronts, you have a lot of electrons and you have a lot of neutrals. And so this makes it so that collisional cooling is very efficient. And so as these ionization fronts are moving through the universe, you're injecting a lot more heat than the final temperature that's achieved behind the ionization front. And most of that is being radiated away as, for example, Lyman alpha photons. And the property that's most important for determining the temperature behind these ionization fronts is how quickly the ionization fronts are moving through the universe. And so you can estimate, based on the sizes of the structures that we expect during reionization and the duration of reionization, what speeds for these ionization fronts are expected. And the conclusion is that the ionization fronts are going at speeds where the gas will cool to something like 25 to 20,000 Kelvin. And because of the exponential sensitivity of collisional cooling to temperature, it makes it so that it's very hard to heat the gas well above 25,000 Kelvin just because the ionization fronts are not moving fast enough. Also, it's hard to cool below 20,000 Kelvin because collisional cooling isn't efficient enough. Okay, so that's the first principle. Okay, principle 2 is that, so we've ionized the gas in the universe to 20,000 Kelvin, and then the gas is going to cool. And so there are two main mechanisms that the gas cools by. And so the first, and this is most important at high redshifts, is that the CMB there's just so much energy in it, and especially at high redshifts, and so the electrons inverse Compton scatter the CMB and lose their energy. And this tends to dominate at redshifts greater than 6. At lower redshifts, the adiabatic expansion from the universe starts to dominate. However, any coolant that you would probably guess might be important actually turns out to be important. Like recombination cooling is important at a certain level, free, and so you can't neglect any of these. This is like a result that seems to happen throughout astronomy. That Occam's razor, where you would expect just a couple things are important, never seems to hold. I don't know why, but in this case, it's there are multiple coolants that matter, but Compton cooling and adiabatic expansion are the most important. Okay, principle 3. So we've heated the gas. It's starting to cool because the universe is expanding and because of Compton cooling. But also you're heating up the gas because of photoionization, and so not only is it cooling, but it's being heated by the fact that your gas is recombining, and then as it recombines, it's being reionized. It turns out that this photoheating depends very weakly on the ionizing background that's around after a region has been ionized, and is mostly determined by how quickly the gas is able to recombine. And so when gas recombines, it then so when a hydrogen atom recombines and becomes neutral, then of order 30,000 years later, this is a result we know from the Lyman-a Forest, that it's going to be ionized again. And so how quickly the gas can recombine determines how much heating is put in, not the amplitude of the ionizing background spectrum. And it also because you tend to absorb photons near the ionization potential of the species that is absorbing, the amount of photoheating depends very weakly on the spectrum of the radiation that's keeping things ionized. Okay, so those are 3 principles, and then the final principle is that, and I didn't tell you before, but around the first galaxies, you almost certainly only ionize the hydrogen and 1 electron of the helium. Normal stars don't produce enough photons to doubly ionize helium. And so so we think that helium is doubly ionized later, probably around redshift 3 by quasars. And so this is a movie of helium reionization from a simulation that I did at the end of my PhD. And so these quasars produce these bubbles of helium where they're ionizing the helium from helium-2 to helium-3. And this heats up the intergalactic medium, but later. Okay. But so that's the standard story. But we could be missing some principle. So and there have been a ton of papers about potential heating sources that we might be missing. And all it takes to heat up the intergalactic medium at order 1 above our standard predictions is about 1 eV per gigayear. And so people have claimed that blazars may be able to do this, cosmic rays, galactic feedback, dust absorption, and various other things that are more exotic. Okay, so how does this work? So here are just some toy calculations that of how the temperature of the universe evolves. So so in this panel, this is the temperature at the mean density of the universe, and so in this panel we're ionizing the universe to 20,000 Kelvin. This is the temperature that we expect it to be heated up to by ionization at redshift 9, and then the 3 different curves are just different spectral indices for the ionizing background, varying the ionizing background that's keeping the gas ionized its spectral index by an enormous amount. And so you can see that even though we're varying the spectral index by a huge amount, the temperatures that you achieve later are not that much different. And so the temperature history is not very sensitive to the amplitude of it's not sensitive to the amplitude of the ionizing background. It's very weakly sensitive to the slope. Okay, this is another toy calculation, but here we're ionizing the universe at different times. So this is at redshift 6, redshift 8, and redshift 9. And And so you can see that by late times, the when you've been ionized to has erased, but at certain times it can make a difference. And this is something that we will come back to later in this talk. And then the bottom panel is doing something that I said you can't even do, that is varying the initial temperature that you heat up the IgM by an implausibly large amount. And I would argue that only this curve is allowed. Okay. And this is assuming instantaneous ionization of the gas, and we're going to generalize this to the realistic case of ionization fronts and things being ionized at different times. Okay, so that what I was showing you before is the temperature at the mean density of the universe. But there's a really nice relationship that relates the temperatures at all densities. They tend to have a power law relation. And so what is plotted here is the density of gas in units of the mean density. So this is the mean density of the universe, and then this is temperature. And so the black points are taking a cosmological simulation and randomly selecting 300 particles and plopping them down. And you can see that they fall very well on this relationship at redshift 4.5 and even redshift 3. There's some dispersion, and this dispersion is from shock heating. So some gas particles shock. But if I did this at redshift 0, there would be a lot more shock heating, and that would be what we call the warm-hot intergalactic medium. So I can also do a calculation where I turn off shock heating. So the red line is no shock heating, and you get this near perfect power law. And so without shock heating, all of the gas in the universe, except the gas that's fallen onto galaxies, would fall on this relation. It's kind of miraculous. And so recently I wrote a kind of a cute. There was a seminal paper by Hui and Genetin on this, and a cute follow-up paper to that explained kind of why this relationship takes the form that it does. So the reason the gas falls on this perfect power law, so the power law has scales as density to the 0.6, which you would say, okay, that's adiabatic. So this is just adiabatic processes that are setting this relationship. But it's not the case because you're always photoheating the gas, and the photoheating is causing gas to ascend to higher and higher adiabat. And so the reason for this relationship is because the photoheating, its temperature dependence, has just the right form that you're always taking gas at different densities to the same adiabat. And so this makes it so that even though structure formation is very messy, how a particle gets to this density, it could have a very varied trajectory, like in its history before arriving at that density. But because you're always ascending from one near adiabat to another, the density history of your particle, how that affects the temperature, just drops out. And so kind of a cute paper explains this relationship, which is important for the rest of this talk too. Okay. So first application. So we're taking these temperature models. I gave you the background. So that was the standard story for the temperature. And we're going to apply them to three things. And so the first thing that we're going to apply this to is modeling some recent temperature measurements of the redshift 2 to 4 intergalactic medium. And this was led by a student of mine, Phoebe Upton Sanderbeck at University of Washington. And so I first should tell you how the temperature of the intergalactic medium is measured. And it's from, as you probably imagine, I told you before, that is from the Lyman-a Forest. And so this is the transmission in a Mach skewer of the Lyman-a Forest, and from a cosmological simulation. And what I'm going to show is varying the mean temperature of that simulation over a very large range. And you're going to see that the widths of lines change as the temperature evolves. And so the widths of lines become wider, principally because of the thermal broadening of the Lyman-a Forest. And this panel is going to show you the power spectrum of the Lyman-a Forest, which measures the fluctuations in the spectrum. And so you will see that as the temperature goes up, the fluctuations will go down, especially at high wave numbers. And so it's this effect on the power spectrum that people are using to measure the temperature of the Lyman-a Forest. So as temperature goes up, the width of lines increases. So here is a compilation as of 2010 of all of the measurements of the temperature from the Lyman-a Forest that had been conducted, so this might be a total disappointment to you guys because it looks like a mess. So this is as a function of redshift, the temperature at the mean density of the universe, and you can see that there's a huge amount of scatter. Although the error bars are really large, so maybe I can draw a line, but there's not a lot that I can learn from these measurements. And I should say most of these measurements were done around the year 2000, and only used a handful of these high resolution spectra. The black points was a measurement that Lars Hörnquist and I were involved with that used more of the spectra, but things are confusing. It's not clear that, and I'm not putting models on this, but it's not clear that we have precise enough measurements to really interpret this in the context of the models I was describing before. And so in 2011, this seemed to change a bit. And so George Becker, who has access to better data than any of us, published a measurement. And so this was his measurement of the thermal history of the intergalactic medium. And he did something that was slightly different than what people had been doing before. And so what is shown is not the temperature at the mean density of the universe, but is the temperature at some specific density with respect to the mean. So this is six times the mean density, and by high redshifts, the density is close to the mean density of the universe. Where he's measuring the temperature, and the reason that George chose to measure the temperature at an evolving density threshold is that the Lyman-a Forest is not sensitive to the temperature at the mean density, especially at low redshifts. It's really sensitive to to temperatures that are coming from overdense regions. Those are the lines, slightly overdense regions that are where you're more easily able to measure their broadening at lower redshifts. And so George made this measurement, but he wasn't able to estimate what the temperature at the mean density of the universe is, because he found that he was only sensitive to the temperatures at these densities. And so in order to extrapolate his measurements, he had to assume some power law relationship that takes the temperature at the densities that he's sensitive to the temperature at the mean density of the universe, which is what everyone else had measured. Depending on what power law he assumed, he would find different things for the evolution of the temperature. Oh, and I should also say that various other efforts have confirmed largely George's measurement, and so there seems to be, at least post 2011, some agreement on how the temperature of the IGM evolves. Okay. And so we wanted to model this, and so this is the previous modeling work was that our work is following is this seminal Hyman and Hui paper, and so that I would claim that here are some models that they had come up with for the possible thermal history of the universe, but they didn't have all of the principles down that I mentioned before. And the measurements certainly aren't as good as they are if we believe George's measurements. Okay, so we want to model the thermal history. And so in order to do this, we heat and cool gas elements based on the simple rules that I gave you before. Before I had shown you how temperature evolved for a gas element that was instantaneously ionized at a certain time. And so reionization is temporally extended. We're talking about these ionization fronts that are moving across the universe. And so and different regions are ionized at different times. And so in order to model the temporal extent of this process, we model the cooling and heating of multiple elements. And so this gives us a range of temperatures at a given redshift. And so in order to compare with the measurements, we found that the mean temperature of these models approximated really well what was measured. The measurement is mostly sensitive to the mean. This was something that was totally not obvious to us. I thought that the measurements would be more sensitive to the lower temperatures in the intergalactic medium, but it turned out that the mean temperature is what they're most sensitive to, and the reason for this, I think, is that in our models the fluctuations, the RMS fluctuations fractional fluctuations are never much greater than 1. And so this means that any way of doing an average kind of gives you the mean. The way the temperature is measured is not obviously going to give you the mean temperature of the intergalactic medium, but if the fluctuations are small enough, whatever weighting it's doing is going to give you something very similar to a mean. And then the final thing that we do, which is may seem a little bit sketchy to you, but if you have problems with it, please look at our paper where we don't do this. I find this is just much clearer to present in this space. Is the measurement is done at a temperature that isn't the mean density, but it's much easier to look it's much easier to understand what's going on if we then extrapolate the measurement using the models to the temperature at the mean density of the universe. And so in order to do that, we use the power law of the models to move the measurement to. So our models give us a power law for how temperature is related to density, and so we use that power law to go from the temperature at a given density to the temperature at the mean density. Okay, and so although that last distinction doesn't matter at high redshift, and so let's first just consider hydrogen reionization. And so we're modeling the heating of the intergalactic medium. Different regions are ionized at different times, and then after the reionization ends, so each of these curves is just different durations for how long reionization spans. And so then after reionization ends, the gas in the intergalactic medium cools, mostly because of Compton cooling off the CMB, and so all of these different curves are different models for reionization, but you can see that they roughly fall within the measured measurement error bars. And so this is the statement that the measurements are really not yet quite sensitive to how hydrogen reionization happens. People are trying to measure the temperature of the intergalactic medium at higher redshifts, and when that's done, if we're able to do that, then the model starts to depart more. But at least at the redshifts where we have temperature measurements, we're not so sensitive to hydrogen reionization. But what we are sensitive to is the ionization of helium. Remember, I told you that helium is ionized, doubly ionized later. And we think it's quasars that doubly ionize the helium. And so we came up with a simple toy model for how quasars heat up the intergalactic medium. And so the toy model, which we found agrees really well with the simulations I had run at the end of my PhD with Lars, is that so we have a quasar, and around that quasar it heats up the intergalactic medium to 8,000 Kelvin or so. And the reason for this is because the low energy photons that the quasars produced are absorbed locally in a helium-3 bubble, but the mean free path of photons that can ionize helium-2 can be very long, and so a couple hundred eV photon can be many tens of comoving megaparsecs. And even and during helium reionization, you tend to absorb even out to keV energies, and so you tend to develop a hard background of long mean free path photons, and so you heat up around quasars to 8,000 Kelvin, and you tend to heat up other gas elements by a comparable amount. And so we came up with a model that approximates this process. And voila, this is the cooling of the IgM from hydrogen reionization for different models. These models are varying the spectral index of the ionizing background. And then when helium picks up, and so these models are assuming the kind of the canonical evolution of the quasar abundances. In fact, we're using a model that Lars and Phil Hopkins came up with that fit the luminosity function of quasars. And I should step back and just say that like a really neat thing is that if you take these models for the abundance evolution of quasars, and you calculate how many helium-2 ionizing photons are produced as a function of time, you get just about the right number to be able to doubly ionize the helium around redshift 3. Precisely when observations, such as the temperature of the intergalactic medium, are suggesting that helium reionization happens. And so we're taking the abundance, these abundance measurements of quasars, and if you use those to predict how the temperature of the intergalactic medium evolves, it's in accord with these measurements. And these two panels, so this panel varies the spectral index of the ionizing background that's keeping the hydrogen ionized. And we found that this was one of the biggest dependencies that had the biggest effect on the temperature of the intergalactic medium. But we also varied other parameters. In our paper, and largely if you assumed that quasars are ionizing the helium at this time, it is able to reproduce these measurements very well. There has been there is some controversy in this field. People have claimed that there might be more quasars at high redshift than some of these models are indicating, and so there's been a lot of work on whether maybe there are more quasars at high redshift. And what we find with our modeling of the thermal history is that if we put more quasars at high redshift than most models are suggesting, then we just heat up the intergalactic medium too early. And so I think these temperature measurements are really consistent with this picture that helium reionization is happening around redshift 3. And then you can see that there's not a lot of room for excess heating. Like these models agree very well with the measurements, and so then you can put constraints on many of these more exotic sources that people have hypothesized could be heating up the intergalactic medium. Okay, so that's first application. Second application, and this is my favorite application of the three I'm going to discuss. We're going to talk about the higher redshift Lyman-a Forest. This is work led by a postdoc in my group, Anton Daloisio. And so so what we're talking about now is the redshift 5 to 6 Lyman-a Forest. Before we were talking about redshift of 4.5 to 2. And so these are some of the highest quality Lyman-a Forest spectra that we have at these redshifts. So these are 7 different spectra. This is the dashed curves bracket the wavelength range that corresponds to the redshift range 5 to 6 in the Lyman-a Forest. And one thing I'd like to just point out is that there's huge amount of absorption in this spectra. There's a lot of transmission here. There's a huge amount of absorption, a lot of transmission, etc. There's huge scatter from sightline to sightline in the Lyman-a Forest at these redshifts. There are even some regions, so here's a famous Gunn-Peterson trough. There's complete absorption. If you look, this is a 150 co-moving megaparsec region in the universe. If you look at the Lyman alpha, which is the black, there's no detected transmission. However, if you look at Lyman beta, which doesn't saturate as easily as Lyman alpha, so this is the same region, same gas that's absorbing here, and Lyman alpha is absorbing Lyman beta here, then there are transmission spikes all over the place. which is telling us that the gas here is still highly ionized, even though it's completely opaque. And so the question I'm going to try to answer is, what is driving these huge fluctuations? The complete opaque in Lyman alpha here, a lot of transmission here. And the story at lower redshifts is that the fluctuations in the Lyman alpha forest are driven by the density of the gas in the universe. So what the Lyman alpha forest is probing is the amount of H1. And so the Lyman alpha, the amount of H1 is in photoionization equilibrium is proportional to density times the recombination coefficient, which depends on temperature, and divided by the photoionization rate, which is telling us about the background, the UV background. And so the canonical story is that this is what dominates. These don't matter. I can ignore temperature fluctuations, photoionization fluctuations, and I can explain the Lyman alpha forest at lower redshifts really well. This is why people use the Lyman alpha forest to constrain, or this is why people are able to use the Lyman alpha forest to constrain cosmology. Because temperature and photoionization are things that are harder to model than density. But it turns out that at redshift 5 and above, density fluctuations can't account for these fluctuations in the transmission of the Lyman alpha forest that are seen. And so the dash curve here is a model that is if you only assume density fluctuations, and you just have to run a cosmological simulation. There's no modeling involved. The histogram is the observations, and so you can see that density fluctuations are become a worse and worse approximation for the transmission. And let me step back a second. What the transmission PDF here is if I take my spectrum that I showed you in the previous plot, and I partition it into a bunch of 50 over h megaparsec regions, then and then I take a cumulative PDF of minus the log of the transmission. That's what is being plotted here. So it's a measure of opacity fluctuations in 50 over h megaparsec regions in the universe. And if I take a model that only includes density fluctuations, it undershoots terribly at explaining the opacity fluctuations we see in the Lyman alpha forest. And so the question is, what could explain these opacity fluctuations? And I'm going to give you, I'm going to give you this. I'm going to explain how these opacity fluctuations could be from temperature fluctuations, from the fact that different regions in the universe were ionized at different times. And so what this plot shows is if I'm ionized at redshift 6, so ionization front is sweeping over the universe. If it hits me at redshift 6, then by redshift 5 to 6, I haven't had a time to cool very much after I'm ionized to 20,000 Kelvin. However, if I'm ionized above redshift 9, then I've had a lot of time to cool, and so I will have cooled to a couple thousand Kelvin. And so there's a huge range in temperatures that you expect the intergalactic medium to have at redshift 5 to 6. And because the amount of H1 is proportional to temperature to minus 0.7, cooler regions are going to have a lot more H1 than regions that are hotter. And so you can, and so in order to model this, you have to do something that you might think is really messy. You have to model the topology of reionization. But kind of a racket in this field is that there's been a lot of work to simulate reionization doing these really detailed, computationally expensive radiative transfer simulations. But people like Lars Hernquist and myself and Matthias Arriaga, Steve Ferlanetto have worked a lot on models where where you try to predict the structure of reionization from just how galaxies cluster. We understand really well how galaxies cluster, and when you compare these models for reionization based on how galaxies cluster to these radiative transfer simulations, they agree very well, ridiculously well, I would say. And so this is a model for the topology of reionization based on the clustering of galaxies on large scales. And so the red regions are regions that are ionized earlier. The blue regions are regions that are ionized late. And so then you can send skewers through this to calculate the Lyman-a Forest, what it looks like. And so this is one such skewer that has almost complete absorption. The dashed is the redshift of reionization along that skewer, that different regions were ionized. And so this skewer was ionized somewhere between redshift 10 and 12, relatively high redshifts. And because it's high redshifts, the gases had time to cool to relatively low temperatures by redshift 5.5. And so there's almost no transmission. However, if I go to a region that was ionized really late, so it didn't have much time to cool, then there's a lot of transmission. And so then you can use these type of models to predict the PDF of these opacity fluctuations, like this cumulative PDF. And so the different curves here, the dotted is just density fluctuations, so the standard model. And then the different lines are the dashed line is a reionization history. So this is the reionization history. Ionized fraction is a function of redshift for reionization history that spans redshift 6 to 10. The red is a really prolonged reionization history, redshift 6 to 12, and the dashed green is 8 to 14. And so you can see that depending on when things are ionized, sometimes you're able to get a lot of opacity fluctuations from these large temperature fluctuations that you expect from reionization. And in fact, if reionization is very extended, then you can almost perfectly match the width of this PDF. And a really neat thing is that this red curve that matches the observations pretty well. This model has almost no freedom in how these fluctuations evolve with time. That's just how the IgM cools after it's being ionized. We have no freedom, but we're able to match the redshifting of this PDF, which when we found this, we're really excited. And so if reionization is very extended, if it starts above redshift 9 and it ends at redshift 6, then that might be the reason for these large opacity fluctuations in these Gunn-Peterson troughs in the Lyman-a Forest. There's only one other possibility. So it's either temperature that's driving these opacity fluctuations, or it's photoionization rate fluctuations. So what are photoionization rate fluctuations? This is from the fact that galaxies in the universe are inhomogeneously distributed, and so the radiation from these galaxies will propagate out in the intergalactic medium. But if you're closer to galaxies, then there will be more radiation than if you're farther away from galaxies. So in practice, the level of these fluctuations depends on how far radiation is traveling. If the mean free path of ionizing photons is really long, then a point in the intergalactic medium sees many different galaxies, and so photoionization fluctuations are small. If the mean free path is short, then there aren't very many galaxies in that region that a point sees, and so these photoionization fluctuations are larger. And so this is another way you might be able to explain the Gunn-Peterson troughs. It's the only other possibility. It's either temperature or it's photoionization fluctuations. And so we and some others have worked on whether these could explain the opacity fluctuations that are seen. And one of our conclusions is you need larger photoionization fluctations than you need temperature fluctuations. It's less natural in a sense, because it's overdense regions in the universe where the sources are, and the transmission is mostly coming from voids, and so it's harder to get the photoionization fluctuations to the level that you need. And so what people have concluded is that you need really short mean free paths for photoionization fluctuations to be the reason. At redshift 5.5. For the reason that this gives you much larger fluctuations, or you need quasar-like sources. I would argue that it's hard to have quasars at these redshifts because we see that quasars are ionizing the helium at redshift 3. If you put a lot of quasars at redshift 5.5, that's going to happen a lot earlier. And so it's hard to see quasars being around and the reason why the photoionization being the driver of photoionization fluctuations. And then there are some observations that suggest that the mean free paths just can't be this short. And so right now, I favor that my favorite explanation for the opacity fluctuation in the redshift 5 to 6 Lyman-a Forest is that it's these temperature fluctuations. And if it's these temperature fluctuations, as I mentioned, it means that ionization is very extended, ending at redshift 6 and half ionized. Redshift like half of the universe has to be ionized at redshift greater than 9. If it's intensity fluctuations, there are also interesting implications. Okay. And then finally, as I told you, I'm taking these temperature models and I'm applying them to 3 things. And so we've done the temperature measurements of the redshift 2 to 4 intergalactic medium. We've done redshift 5 to 6 Gunn-Peterson troughs. And finally, I'm gonna tell you about how the IGM temperature affects the formation of dwarf galaxies. And since I don't have a lot of time, I'm just gonna sketch this research. And if you're interested, please just see the papers that are cited. Okay. So the dwarf galaxies, where there are these ultra-faint dwarf galaxies in our local neighborhood that have garnered a huge amount of attention in the last few years. And so here are here are some color magnitude diagrams of some of these. Each of these points are different stars in these dwarf galaxies, and then the blue curve is isochrone, where the width, the mean is 13.7 gigayear, and the width is plus or minus 1 gigayear. So you can see that the cutoff in the main sequence that is occurring roughly where you would expect if the stellar populations in at least these ultra-faint dwarfs formed in the first billion or so years in the history of the universe. And this is generically true, that the stellar populations in these ultra-faint dwarfs, a lot of their stars had to form in the first couple billion years. And so there are 2 hypotheses for what sets the minimum size of galaxies. So these are the smallest galaxies we observe, and so these are the ultra-faint dwarfs are being most affected by how galaxy formation is suppressed. And so one hypothesis is that it's internal feedback processes within the galaxies themselves, such as supernova or stellar winds. And the other hypothesis is that the minimum mass of galaxies is set by the temperature of the intergalactic medium. And I think if you asked a simulator of galaxies, what they would tell you is that both of these are important. When they simulate ultra-faint dwarf galaxies, the IGM temperature and the internal feedback affect what masses and stellar masses they have as a function of halo mass. And one reason people like the IGM temperature is that you might think it naturally predicts that the old stellar ages, because you have these ionization fronts that are moving across the universe, and you're heating up the IGM, and this is dramatically increasing the Jeans mass of the intergalactic medium, which means that pressure is making it so that gas does not fall onto halos as easily. However, the models for how the IGM temperature affects the galaxy formation are really simplistic, and so they are basically based on this Jeans mass criteria. So I put Jeans in quotations because sometimes the Jeans mass is calculated in a way that includes the expansion of the universe, and this is called the filtering mass. But you're essentially taking a mass scale, the Jeans mass, where pressure is able to counteract gravity, and evaluating it at different densities. And so either at the mean density of the universe or at a density that's 200 times the mean density of the universe, the density of halos. And what you ask is the mass of my halo greater than this Jeans mass? If the mass of my halo is greater than this Jeans mass, then a galaxy forms. If it's less, a galaxy doesn't form. So that's how semi-analytic models generally model the effect of the IgM temperature on galaxy formation. And so I'm gonna present just kind of an intuitive picture for how this really happens, how the temperature of the IgM really suppresses galaxy formation. And so what is plotted here is the temperature of a gas particle, and on the x-axis is the density. And in this temperature density plane, there are a lot of neat contours that you can put. And so this is the Jeans mass, so of the gas at that temperature and density. All of the dotted curves. The dashed curves are different adiabats. The solid curves are the density and temperature at which cooling becomes efficient, collisional cooling, for different values of the ionizing background. This sets how much hydrogen and helium is around, so that enables you to cool. And then you could also put where gas self-shields and where cooling becomes more efficient. Okay, so I'm going to paint a very simplistic picture, but then one that we're about in the next slide we'll test with cosmological simulations for how temperature affects the evolution of collapsing gas particles. And this simplistic picture is going to be in the spherical collapse model. And so at the time of reionization, a gas particle is heated up to 20,000 Kelvin. And in this case, I'm drawing the evolution of a gas particle that's collapsing at redshift 6. So it's collapsing onto a halo at redshift 6, and reionization occurred at redshift 10. And so if I'm a spherically collapsing region with those parameters, then I have this density at redshift 10. I'm heated up by reionization. It turns out that at redshift 10, I'm also at turnaround. And so then if my mass is greater than the Jeans mass, the mass of the gravitational potential well I'm falling into, then I'm able to collapse and cool and form a galaxy. And so the criteria for whether a galaxy should form should be whether along this trajectory, whether my halo mass is greater than this Jeans mass of the intergalactic medium. If I calculated the Jeans mass at the mean density of the universe, my Jeans mass would be evaluated here. My gas particle never gets even close to the mean density of the universe. Okay, so here's another case. So I'm a gas particle that's ionized at redshift 10, and then but I collapse at redshift 3. This is the trajectory I would follow. And so if the halo I'm following on is greater than the Jeans mass at every point along this trajectory, that's how I would evolve. And then you can even do this at redshift 0, and you would get something like this. And because we're well after 5 p.m., I'm just going to really sketch things now. And so you can go into a cosmological simulation and you can test this. And that's what these trajectories are. These are different particles that are falling onto galaxies. And if you looked hard at the caption, it's a little bit hard to read. Then you would see that it's comparing the maximum Jeans mass along a trajectory to the halo mass. And so then. And so that simple picture that I gave you, we tested in cosmological simulations, and we showed that it works pretty well. And then we also outlined a way to incorporate this prescription into a merger tree, that in order to produce how much gas is falling onto halos of a given mass. And this is I think what semi-analytic models of galaxy formation should be using rather than these Jeans mass criteria. And so that takes me to my conclusion. So after 2010, we have these better measurements of the temperature of the intergalactic medium from the Lyman-a Forest, and they seem to be very consistent with our vanilla IgM model for how the temperature evolves, with helium reionization later, and they're also consistent with the temperatures we would expect for almost any reionization scenario. Then at redshift 5.5, we see these Gunn-Peterson troughs, and they either owe to fluctuations in the photoionization rate or fluctuations in the temperature of the intergalactic medium. And I argued that I think it's the temperature, and if it's the temperature, it really has some interesting consequences for when reionization happens, which is something that we don't know. And then finally, I outlined kind of an intuitive model that, in my opinion, for how the thermal history of the intergalactic medium affects galaxy formation, that I'm hopeful will be incorporated in semi-analytic models of galaxy formation. Okay, thank you.
Working? Yeah. So thank you, Matt, for a great talk. So we have time for some questions if anybody has any.
You just disappeared. All right. So
Sorry,
I wanted to.
It'll really come up in a
That's okay.
second.
So
Okay.
in your point about temperature fluctuations versus intensity fluctuations.
Yeah.
So the mean free path that you were talking about was megaparsecs.
Yeah, that's right.
So I guess what you are assuming is that the escape fraction of each source is the same. But you could imagine that internally, the escape fraction changes from source to source. And in that case, you might be able to reconcile a bit better, right?
So the fluctuations are not set very much by the abundance of sources, for example, which I think, like if I turn the escape fraction off in some of these sources and on in others,
right?
Or just because there are so many, the fluctuations are driven by the cosmological fluctuations and how galaxies trace the large scale density rather than the Poisson and the fact that you're having only a few galaxies.
But if you're switching on and off, then you're changing the distribution, right?
Yeah, but you have to switch them on and off in order for them to have a quasar-like abundance. So people have shown, actually our group has shown that unless they have they're as rare as quasars, you cannot get the level of fluctuation.
But then you can put constraints on how much this escape fraction could change from source to source. There is a lot of debate whether, depending on the angle.
Yeah, that's right. We thought about this a little bit, and so you would have to have escape in some of your galaxies that is much greater than 1 in order for this to work.
Oh, okay. That's
why
impossible.
Because they have to be so rare that the escape is huge.
Got it.
Yeah.
I want to ask you a question because there is one key assumption in this talk.
Yes.
And that is that reduction in transmission is just due to reionization. But what about the fact I'm not hearing, which is the temperature of the triple point of hydrogen? Because when the universe drops to the triple point, then all of the clouds of hydrogen gas should be crystallizing out. They should be snowing out into stellar medium on the whole, or something of that kind. So there's another mechanism that's operating in the same redshift range between 3 and 8, where there's another process that's causing a change in the transmission or the opacity of the universe.
But so this is an ionized plasma so I don't see the.
Well, the temperatures are a very vague thing here. This is not about an equilibrium situation between a cloud of gas and the temperature of the cosmic background. So far from equilibrium.
No, it's pretty. So the equilibrium times, so let's say put in an electron that's super thermal. It will Coulomb via Coulomb losses. It will become. It will thermalize on a time scale much shorter than the time scales we're talking about, because we're talking about billions of years. Like redshift 6 to 2 is 2 billion years, and so the approximation of things being thermal, at least at these redshifts, is reasonable. Things eventually become very low density in the universe, and so you can have your protons and electrons kind of decouple in certain places and have different temperatures. So you can have a 2 temperature because the energy interchange time scale is longer than the time scale for your electrons themselves or protons to thermalize. But this is not it's not hugely out of equilibrium.
Thank you. I may have taken.
But yeah, okay.
Thank you.
Anything else? Not, let's thank Matt again.